In my previous video on the central limit theorem, I explained why this bell-shaped curve comes up when you add up sums of random variables like dice rolls or coin flips or any other random variable you want. And I explained why it has to have this special shape, e to the minus 1/2 x squared. But that's not the whole story, because the actual density function is not just e to the minus 1/2 x squared, it's actually 1 over square root of 2 pi e to the minus 1/2 x squared. Why is pi here, and why is it square rooted? Well, one very simple answer to this question is if this is going to be a proper density function, it has to integrate to 1. So if you find the total area under the entire bell curve, it has to be equal to 1, representing a 100% chance for the random variable x to be somewhere at any given time. And of course, you can then use pure integration to find this square root of pi. And in fact, this video was partially inspired by this meme I saw of people doing exactly that. So taking the exponential function e to the minus x squared and integrating it through a long sequence of steps. And they really did it step by step, doing change of variables, doing this determinant trick to change to polar coordinates. And after a lot of cranking out, finally coming out with the square root of pi. And I also saw this when I was a student. It was one of the first examples everyone sees of changing variables, but it's a little bit hard to intuit like what is actually going on. In this video, I'm also going to find the 1 over square root of 2 pi, but I'm going to try to do it a little bit more probabilistically. So thinking in terms of random variables and probabilities, can we add some intuition to this kind of proof? So let's pretend the 1 over square root of 2 pi is some unknown constant c, and let's try to prove that c has to be 1 over square root of 2 pi. And the surprising fact about random variables that's going to help us figure out the c is that if you take 2 copies of a normal random variable, so not just an x, but an x and a y that are independent Gaussians, so they now have this like 3D density function going on. So we have x and y kind of living in the plane, and the height of this function over here represents how likely any individual point is. And the really surprising fact about x and y together that explains this constant c is a connection between x and y and other families of random variables. And specifically, if you take x and y and you square them and add them together, so you look at x squared plus y squared over 2, this is a new random variable. Let's call it the name u. It's a positive random variable. X squared is positive, y squared is positive. You could calculate its average. X squared on average is 1, y squared on average is 1. So x squared plus y squared divided by 2 on average is also 1. So this new random variable, what is it? And it turns out that it's actually our old friend, the exponential random variable. So even though x is kind of complicated and y is kind of complicated, when you square them and add them together, that is actually just an exponential random variable of mean 1. The statisticians will refer to this as saying chi-squared random variable with 2 degrees of freedom is equal to an exponential. And I had already gotten my PhD in probability theory when someone told me this fact, and I thought it was so crazy. I was like, for sure you're wrong. And I think I bet them a lunch that they were wrong. And then we did the calculation. Of course, they're right. It's a very surprising fact if you've never seen it before, and it has a really nice, simple picture proof, and it's also going to explain why c equals 1 over square root of 2 pi. The starting point is to look at the density function for x and y together. So we have the density function for x on its own, because x and y are independent Gaussians. To find the density function for both of them together, we multiply their density functions. So the density function for x and y together is the density of x times the density of y, and it is simply 2 copies of our formula. C e to the minus 1/2 x squared times c e to the minus 1/2 y squared. We can simplify this a bit so the c's can come together to make a c squared, and then we can bring the exponentials, instead of multiplying them, we can add the exponents. So it's c squared e to the minus 1/2 and then x squared plus y squared. And this is where your brain should start thinking in terms of geometry and pictures. What this means is that if you want to know the likelihood of any individual xy point to be chosen by this pair xy, the only thing that matters is not the value of x and y individually, but the sum of the squares, x squared plus y squared. And geometrically in our picture, x squared plus y squared has a very nice geometrical interpretation. It is simply how far away is the point xy from the origin. What is the radius of that point? So if we call x squared plus y squared, we call that r squared. What this is saying is if you look at like a circle of radius r in the xy plane, then every single one of those points, they have exactly the same probability density. And that is why the picture has this circular symmetry, right? You can sort of spin the picture around and it doesn't look any different because all of the points in a circle have the same exact likelihood to be chosen. This lets us do a very nice calculation. If you calculate the probability that x and y is chosen somewhere in the circle, well, all of those points have the same value. So the probability density is very simple. It's just c squared e to the minus 1/2 r squared, where r is the radius of the circle that you picked. That tells you the height, the probability density. And then to figure out the true probability, If you want to know the true probability, you have to multiply it by the area. What is the area? Well, that's where pi comes in. It's 2 pi r times dr, where dr is the infinitesimal thickness of this circle I have drawn over here. So to convert the probability densities into a true probability, you have to multiply by the area, and that is where pi appears. You might notice there's a c squared, there's a 2 pi. We're getting close to what we want of showing that c is related to the square root of 2 pi. But let's not get ahead of ourselves here. Let's try to figure out how we can manipulate this calculation to get what we want. Well, when we look at the right-hand side, c squared e to the minus 1/2 r squared, and then an rdr at the end, you should start to think in terms of change of variables. And the change of variables here that is very natural is to let u be 1/2 r squared. U is 1/2 r squared makes a lot of sense because that is what is appearing in the exponential. And not only that, if we do the derivative by chain rule, du will be rdr, and that is what is appearing in the dr part. So this change of variable sort of naturally fits into our calculation in two different places. The rdr gets replaced by a du, and the 1/2 r squared gets replaced by a u. And we have this very simple looking formula, c squared e to the minus u times 2 pi du. We can group all those constants together to put 2 pi c squared in the front. And now we have noticed that the whole calculation has simplified down to just one single function, e to the minus u. Very nice. What have we actually calculated here? Well, we've said what's the probability that xy is in the circle, but then we did this change of variables to u, and u is 1/2 r squared, and r squared is actually x squared plus y squared. So what have we done after we unpackage all this? We have calculated the probability that x squared plus y squared divided by 2 is equal to u up to this infinitesimal du. So x squared plus y squared over 2 has to be somewhere in the range u to u plus du. It depends only on u through e to the minus u times that infinitesimal du. And this calculation is exactly what we call a probability density function. We've calculated the probability density function for x squared plus y squared over 2 using a geometric picture. And the answer is the density function is e to the minus u. But wait a second, e to the minus u, that's the density function for an exponential. So what we've proven actually, this calculation shows that x squared plus y squared over 2 actually must be an exponential. That's what we wanted to show. Very nice fact. We can now finally figure out what does the constant c have to be. Well, if we look at the equation that we have for the density of x squared plus y squared divided by 2, on the left-hand side, we have a true probability density, and on the right-hand side, we have a formula involving e to the minus u. Now, what we can do is we can integrate this thing over all the possible u values from 0 to infinity. On the left-hand side, we have the integral of a proper probability density function. What's the integral of any density function? It always has to be 1. And on the right-hand side, you have the integral of e to the minus u. What's the integral of e to the minus u? Well, its antiderivative is also e to the minus u. You plug in 0, you get 1. So our formula showing that x squared plus y squared over 2 is an exponential actually comes with this constant 2 pi c squared. And when you integrate out, what's left is only that constant 2 pi c squared. And so it must be that 2 pi c squared is equal to 1. And if 2 pi c squared is equal to 1, then c squared is 1 over 2 pi, and c is 1 over the square root of 2 pi, which is exactly what we wanted to show. And if you compare this proof to the original meme that I showed, you'll see that actually all of the steps are mathematically sort of the same. We do the same trick of x squared plus y squared, doing a change of variables, figuring out what the integrals have to be. But this way, it kind of gives it a little bit more probability, meaning you have a new random variable x squared plus y squared over 2. And the interesting thing is that this random variable is a nice exponential. This is what I love about math on YouTube nowadays, is that we've taken all these old proofs that are really classical and are like in all the textbooks, and we've added color to them and animations and given them the extra love that comes from a nice visualization. And if you want to take things even one step further, you can make your math interactive by using the sponsor of today's video, Brilliant. Brilliant helps you get smarter every day with thousands of interactive lessons spanning everything from math to science to programming. Their interactive puzzles help you build your skills through hands-on problem solving. This kind of active learning has been shown to greatly improve learning outcomes. Their mix of engaging problems, competitive features, and daily encouragement keeps you motivated and on track. I'm particularly impressed by their latest courses on how AI works. It's amazing to visually see how the math you learn in math class can be used to create these AI systems. Whether you're just getting started with learning about AI, or you're an expert who wants to deepen their understanding through next-level interactive visualizations, Brilliant's got you covered. To try everything Brilliant has to offer for free for a full 30 days, scan the QR code on screen here, or you can click on the link in the description below. You'll also get 20% off an annual premium subscription. Thanks to Brilliant for sponsoring this video.